Okay. Shear example 4. So in this example we're considering a welded box beam, and it's been fabricated by welding 20mm thick flange plates to a 12mm thick wet plate using fillet welds. We have the maximum shear force on the beam, which is 1750 kilonewtons. So the design shear force is 1750. And if you had a simply supported beam with a point load on, then the point load would need to be twice 1750, which would be 3500, in order to lead to two reactions of 1750 kilonewtons and 1750 kilonewtons, which would then lead you to a shear force diagram something like that, where that bit there is 1750 kilonewtons. So if we had done a cut in the beam at any position, there would have been equal and opposite shear forces. Obviously they would need to cancel each other out just by making an arbitrary cut, and the value of the shear force is 1750 kilonewtons. So that would be the shear force that needs to be designed for if that had been caused by a 3500 kilonewton force in the center of a simply supported beam. So it says determine the maximum shear stress in the web, and then determine the demand on each weld in units of kilonewton per millimeter length of weld, choosing appropriate weld sizes. So let's draw out the section first. So we've got our beam, which is going to be like there. So that's probably not to scale. Never mind. And at the bottom there, we would have the other bit at the bottom there. So we've got some. Let's say we've got an overall depth of 600 millimeters. So from top to bottom, that's going to be 600 millimeters. Let's just say that the breadth of the first plate is going to be 300 millimeters, and I might want to call that B1. And then the thickness of the top plate is going to be 20 millimeters, and I might want to later refer to that as T1. And then for these longer bits here, we've got the depth of the section down there. So I'm going to say that one is going to be 600 millimeters minus 20 minus 20, which is going to be 560 millimeters. And then later on I might want to call that I'll just call that D2. And then the thickness of each of these is going to be 12 millimeters, which I might want to call T2 later on. Just put those in brackets. Now, we know that line is going to be the neutral axis of the beam, and we know that the neutral axis by symmetry, from the top of the beam to where the neutral axis is, that's going to be big D over 2, which is going to be 300 millimeters. And then we also know the distance to the bottom bit, just extending that line there, and that's also going to be 300 millimeters. So let's go through the strategy. Step 1, let's calculate second moment of area of the beam about the neutral axis, because we're going to need those terms later on. Step 2 is going to be the design. Step 2 is going to be the calculation of the stress at the center of the beam. So if we go back, so we'll call that I. That's the second moment of error. So if we go back and we looked up, we would have tau as a function of y is going to be equal to v times s dash y divided by I, and b as a function of y. So if we wanted the maximum value, firstly remember that the neutral axis is where there's going to be the origin of the y-axis. So again, not that it matters, because it could have gone anywhere along the length, but we'll just say our y-axis is going from there, although equally the y-axis could have been drawn from here. Okay, so but it doesn't make any difference. But we'll just assume that the y-axis goes up from the center of the neutral axis. Although, as I said, it could have been here or it could have been here, because we're just reading off the values of y, so it doesn't really matter. So we will then get tau max, which is what we're looking for, determine the maximum shear stress in the web, and the maximum shear stress in the web must occur. It must be equal to when y is 0 millimeters. So at the neutral axis, the shear stress would be maximum, and that would be equal to v s dash y, which would be at 0 millimeters, and that would be equal to I, and that would be multiplied by b as a function of y, which also would be at 0 millimeters. So we're talking about stresses, and we're not talking about about forces. So hopefully it should be obvious that just draw a smaller to scale. Suppose that I had the webs here, and then it should be obvious that the value of I wouldn't change, and suppose I'd even decided to push the two webs together so that they're just touching, or there's only a small difference. The value of I is not going to change, and the values calculated are not going to change either. So B, in this case, because we're talking about a stress, that must be equal to 24 millimeters in this case here, or T2 plus T2, because we're calculating a stress, so we do need to take into account both webs and in additive manner. And then the S dash Y, that's going to be the neutral axis again, and then again there, so the neutral axis. So we're just going to be calculating, and then I'll just draw that there, and then that line there is the neutral axis. So we're just going to be calculating the first moment of area of the neutral axis. So if that area had been A1 and then that area had been A2, it would be A1 multiplied by that distance to take you to the centroid of the first shape, plus A2 times that distance there to take you to the centroid of A2, and then of course plus another A2 times that distance there, exactly the same distance there, and that would then give you the value of S dash at the neutral axis, and the value of V is going to be 1750 kilonewtons. And I we would have calculated before in the previous step, and I might as well tell you that when I is calculated, it does come out to be 1.361 times 10 to the 9 millimeters to the fourth. So that would be step 2 of the calculation. So the important bit here is you need to be aware that since we're talking about stresses, when we substitute B at 0 millimeters at the neutral axis, we do need to include both breadths or both thicknesses of the of the web.